Thank you, everyone. Dan, if you just want to move on to the next slide, please. ETEL is a New Zealand-based manufacturer of distribution transformers mostly. We've been going since 1994. Just before that, we used to be part of a company called ETE, which made smaller power pack type transformers. And out of that, we were asked to make distribution transformers. So we made one in 1994, and we make around about 8,500, 9,000 with capacity to making more. We have a factory in Auckland and Avondale, and we design our transformers there. So we have a large engineering group, and we have a factory there that we manufacture our oil-filled transformers from. We've always been very flexible in what we deliver to our customers. There's like 29 networks in New Zealand, and just about every one of them wants something a little different. So that's, a little bit of a challenge for us, but it's been an opportunity for ETEL because we have the engineering and design group in New Zealand. We can cater for their differences. So I can go on to the next slide there. So as part of ETE and then part of a separate company, which was set up, and as I say, around 1994, ETEL itself, we have around about 350 employees. We're in 6 sites around the country and also a site in a manufacturing plant in Indonesia. We deliver to 49 different networks, both in New Zealand and Australia and the Pacific Islands. And we have the capacity of making 2,500 MVA per year. So that equates to, as I say, around about 12,500 transformers per year. Okay, we'll move on to the next slide. So just talking about our facilities, we have a manufacturing plant, as I've mentioned before, based in Avondale and Auckland. We have a services group, which is based around the country, Auckland, Hamilton and Christchurch. Our Auckland plant, we take transformers mostly from one of the largest networks, Vector, and we refurbish those for them if it's economical to do so. Not only our own transformers, but transformers from other manufacturers as well. And as I mentioned before, we have a manufacturing plant in Indonesia, which really is to focus on that Indonesian market for us. Okay, we'll move on. As I mentioned before, our head office is in Auckland, as in Avondale. That's where the engineering group is, and the manufacturing plant where we make the majority of our transformers is based as well. You can see that's spread over quite an area, and that since we started off so small, just making 1 or 2 transformers initially, we've sort of grown sort of organically. And what it's meant that is the plant has sort of just expanded, and we've been looking recently at how we actually move our, well, not move a plant, but change the plant so that it's more efficient, because it's sort of bits are being added on rather than being planned right from the start to take the numbers that we're doing now. Okay, move on. So we build transformers ranging from small ones, 1 kVA, single phase, up to 4 MVA, and we can in our plant in Indonesia make bigger transformers as well. We make 11, 22, 33 kV transformers. We can't go any larger than 33 kV transformers in New Zealand, and our manufacturing plant there, just purely because of the physical size of the transformers. As I said, we make about 12,000 units, which is around 1,900 MVA per year. So moving on, that's pretty much just a quick overview of the company. If you have any questions, please just let us know and we can answer those for you. I'll just hand over to Dan to go into the more technical side and probably the reason that you're all here to listen to.
G'day. I'm waiting for the camera to come on me. Cool. So,
no, you're anyway,
good. So yeah, thanks very much for having me here. It's been really nice to be involved in engineering New Zealand. So as a background to myself, so I've been involved in the electrical industry for about 20 years now. So initially I'm from the UK, so I started off, I did my degree in the south of England, and then I moved into working on hardware for communications and avionics for helicopter systems and large vehicles, tanks and things. So I was doing a lot of that work. And then after about 4 years of working in that industry, I thought that power looked at that time in the UK to be up and coming. So I thought I really wanted to move my career from the hardware side over to there. So I thought one of the ways I decided to do it was actually go back to university and do a PhD. So in this time, so this was back in 2004 when I started my PhD, it was with the National Grid. So this is the transmission operator of England, Great Britain, and I was actually looking at the use of vegetable oils as power transformer insulation. So this is what got me really interested in transformers. This is what got me on that track of building my career up with transformers and power, and also looking at things like dielectrics. And in terms of what I was doing then at the University of Manchester, the reason why National Grid wanted to go the way of vegetable oils was to lower their risk profile. So at that time, they were concerned with things like with the mineral oil inside their transformers. There's a lot of it. There was other historical things such as PCBs, which were still on the landscape. And then they are thinking to themselves, well, okay, how do we, in terms of our transformers, lower the risk profile? And vegetable oils were seen as one way to do it. After that, I moved to Melbourne. So there was a project starting up there run out of New South Wales by the Sydney and the main rural distributors, which was Country Energy at the time. And they wanted to use power transformers filled with vegetable oils. And at that time, they were quite keen to know things like on condition monitoring. And if they have this power transformer there for a while, for over the decades, then how does the management of it actually differ from the use of mineral oil? So I hopped on the plane. I jumped on the plane from Manchester and I flew to Melbourne, and I got involved there with the Australians and looking at how do we bring in vegetable oils. And then I started to really diversify in terms of transformers. So I started looking at more life in general, looking at reliability, looking at usage. Now, one of, I suppose, the impactful things which came out from the work I did back then was that the IEC transformer loading guide was updated 3 years ago in 2018. Now, the Aussie and the New Zealand one has yet to catch up with that one, but a lot of the work we were doing in Melbourne went directly into making that standard, so we're listed at the back of the references. I also got involved in university lecturing as well, so I think that's quite important for the industry to liaise and to support academia, in that this is where we get our students from, the next generation. We want students who are useful, we want them to sort of who can fit in, we want them to be able to slip into this industry function quite easily. So I think one way of doing that is obviously for industry to support universities. I was lecturing engineering from 2007 to 2019, so I was doing that at Monash in Melbourne for a couple of years, and then in 2013 I moved to the University of Queensland in Brisbane. I also started to get very into a lot of these professional groups because I think it's a very good way to actually network and to build contacts and to also find out what everyone else is up to. So currently I'm a senior member of the IEEE, so I got that grade through a couple of years ago. And the sorts of things which I've done for the IEEE is planning conferences, it's working with students, it's writing books, it's publishing a lot of articles. Now, at the beginning of last year, so I moved from Brisbane to here, New Zealand, to take up the role in ETEL. Now, going back to what Chris was mentioning about my my Aussie hat. So in Queensland, of course, you have to wear a hat because everyone gets like skin cancer and stuff like that. So that's why the necessity for the hats. And when I got off the plane here, I was wondering what was the equivalent, or what would be the equivalent Kiwi headdress to I suppose a bushman's hat. And somebody told me it would definitely be a woolly beanie. So I was thinking about that. Should I have a photo of a woolly beanie on? But then I found out when at ETEL here, we actually do give out woolly beanie hats to people as our company memorabilia. So we have like the ETEL logo on the top, on the front. So I think in some ways that does demonstrate the point that the person who told me there's nothing says more being Kiwi than a woolly beanie is definitely probably right on that. Another activity I've been doing volunteering has been Seagrace. So it's an international power industry group which is run out of Paris. So it's quite a big global one, although it is more specific on things. So there is a group in it which talks about power transformers, and there's another group which does cables, and there's one which does switchgear. There's all these different things. Now, when I moved to Auckland, I didn't really have my professional network then. I thought to myself, I wanted to get a network up and going as quickly as possible. So as part of that, I set up a power transformers group here. So we meet every couple of months and we just talk about transformers. We talk about what everyone's up to. We talk about specific projects. We talk about interests. And I think for us, it's a very good way of this finding what is the direction of the industry, or what is everyone sort of concerned about. Now, middle of last year, I also applied for my Chartered Professional Engineer grade. I did that when I sort of came over here, and I also got that and became the Chartered Member of Engineering New Zealand. So as I said, it's great to be involved in these institutions, these professional societies. It's just from that networking, finding out what everyone is up to, exchanging ideas. So my role right now, I'm responsible for the innovation engineering at ETEL Transformers. So these are part of my role. It's looking at really what is the future direction in terms of transformers. Now, we can see a big change is happening. One is the coming in of information technology, which maybe if you look back 20, 30 years ago, wasn't really around at all. But then there's also this drive towards renewables and decarbonisation, which is also likely to affect the usage. So I'll come onto these more later on. Now, the first question, I guess, what we wanted to go over in terms of this presentation, and it was really what is the point which we wish to get this discussion going on. It's obviously, if we're talking about how do we think usage is going to change, then we have to really start to think about what are the drivers. What is, if we're having a change coming in, then really what is the driver behind it? What is the need for it? So we then started thinking of some questions. I mean, one of them was, why should the usage change? So if we're thinking of that usage will change, and I believe it will, and I'll go over the reasons in a bit. And then it's the next thing is, why should usage change? So what is the actual driver to it? And then it's, what is the need? And then there's also, I guess, a counter criticism. Like if we're talking about, well, we think transformer uses are going to change, then you might have some people saying, well, why don't we just keep doing everything like it's always done? We're quite happy. We don't feel that the need is there to change. So this is why we like discussion. We like to try and figure out what is the direction we're heading in. So in terms of the imperative, if we're going to be thinking about what changes in usage are coming, so one of the points is that asset infrastructure lasts for decades. So if somebody purchases a transformer, it will last for a very long time. We're looking at decades there. So this is why, even if something is going into now, in this year or something, it is really worth thinking out maybe 20, 30, 40 years into the future. And then just trying to think to ourselves, well, how will the usage change at that? Because we might think to ourselves that something like 2060 is a long way away, but actually a lot of the stuff we're actually producing now is probably going to still be around then. So this is worth, I think, considering the changes, because we can hopefully keep costs down a bit, that if we put something in service now, we're not going to have to replace it somewhat down the track. Now, the next question is, okay, if we're thinking about, right, okay, infrastructure going in now, we want to be looking several decades down the track. It is obviously, why do we think we need to be considering this at this point in time? And I think really with the 2020s, there are going to be quite substantial changes coming around. So if we were to maybe look at, well, in the 2010s, the 2000s, 1990s, when these transformers were going in, probably I guess the philosophy or the design ideas or the network planning then, it was completely appropriate for that time. But the problem is, I think we're seeing now, is that there's just so much change which is actually happening on our energy systems. So we've got this idea of net carbon neutrality by 2050. So this is a government aspiration. It's going to start to maybe look at increasing the uptake of electric vehicles. So therefore we can start to think about, well, probably the load is going to increase. Should we right now be thinking about incorporating that into our planning decisions? And I think that is quite a challenging thing to do, because we don't actually know what the networks will be looking like in several decades' time. So other things we can imagine coming along here. So we have our renewables, probably other things as information technology coming along. Now, I don't really see the information technology as almost like the driver for a change in usage. It's almost that if we expect something to be happening to change the usage, then we might find that information technology is quite a good way to actually help us reduce risk, to actually help us prevent downtime, or even just allow us to see what's happening on the system better. Now, in terms of challenge, I think one of the challenges for us is that simply there's just so many options out there that if we're starting to look at new technologies or we're starting to look at different usages, it can be quite hard for us to really understand what should we be doing now and actually selecting what should we be doing. So I've got these 2 points here. Now, one of the things I'd just like to say here, it wasn't really an either or I put here. This is more of a discussion point. Now, if I had everybody in the room here, I would be asking the question, why do you think that I've concentrated on that too? So unfortunately we can't, it's a webinar right now, so but this is, I would normally ask, and I hope maybe it's a couple of people or maybe thinking in the background, and really, why did I decide these 2 specific things? Now, in terms of really usage, the first point, the improvements to efficiency of resource usage. So what we can start to see here in some ways is really, it's like a slow change, I guess. It's that we have our industrial transformers, we have industry companies. They want to naturally prevent outages, they want to reduce downtime because of the associated loss of output or use. So in some ways, it's not really a step change in how things will be used differently. It's more that these companies wish to steadily improve the bottom line. They steadily wish to understand things such as the risk. They want to reduce downtime. They want to reduce the chances of something going wrong in the plant. So we can see in terms of this change in usage, it's not like a hard change where there's a lot of changes happening. It's more this long-term ideas within companies. And we can think to ourselves, how can we better do it? How can we change, or how can we bring in ideas of what can we do? Now, in terms of us in this whole thing of improving the efficiency of resource usage, then we can really start to see information technology helping us really on this transformer, such as online monitoring, and that it can help us improve this efficiency. Now, the second point in terms of what is the change of usage there, we see as with the government bringing in ideas about decarbonisation. There's also technology such as rooftop PV continues to become cheaper. People want to put rooftop PV on their house. They might start to think about batteries. Now, I appreciate right now that probably the economics of a battery in the house is probably not really there to drive uptake, but it's probably going to be coming because over time technology improves and people might decide that eventually it becomes economically better to have a battery and keep your solar energy yourself rather than exporting it to the grid. And then there's electric transport. Now, this I think is driving a lot of discussion in the industry right now. And on the one hand, it is just an extra load on the transformer. But obviously, nobody really knows where these loads will be. So in terms of the consumer, where do they wish to charge? Do they prefer to charge at home? Do they prefer to charge somewhere like a shopping mall or at work? And when we think about the utility, how do they need to actually be upgrading transformers? So we wouldn't say upgrade everything across the whole network. It's going to be more targeted. They want to start to be looking at where are these electric vehicles charging up, and maybe reinforce that area if they can. So in terms of usage, so I put this in here. So this is more thinking about industry and infrastructure. So this is our large companies. They have transformers on site. They're doing something with them. Then we have our infrastructure, our railways, our bridges, our hospitals, schools, and other buildings like that. So in terms of what is the usage here, we can really see the need here is to drive the bottom line in industry, in that we would prefer it in that the usage of the transformer can change to prevent unexpected downtime, because we want to improve that bottom line. And then in infrastructure, a distribution transformer might be seen as a small part of it. But if the distribution transformer goes down, then there can be a follow-on event. You can have things such as a hospital. You can't have that going offline. Everybody might get annoyed if maybe a transformer supplying the lights to a bridge or to a railway stops working, because then it's those follow-on societal effects. So one of the things we can start to see now with technology to start to push that down is the usage of the transformer. It changes slightly to also include data gathering. Now, what we would like with the transformers within the industry, within the infrastructure, to also now start to collect data on what is actually happening around it. So it's not only of the transformer itself. So if we're going to put some online monitoring on the transformer, it's not only we're looking at the health of that transformer, but we're also looking at everything around it, because we might find if something else is happening on the system, which might start to stress other components. So we might start to see here the transformer itself can start to put its hand up, warn us of any potential problems that it's starting to see around the system. Now, that can be very beneficial if this is happening, because an organization is not going to be taken by surprise. So if the transformer is flagging an issue, then hopefully after acting on it, then the downtime and lost production will be reduced. The engineer also has data on which to manage plants. So we would hope that if problems are being flagged during maybe inspections, during when the engineer is doing something anyway, then we can actually prevent unintended outages or unexpected outages. Sometimes also what we've seen in terms of, well, why monitor a transformer, is that they can be complex systems, and if something goes wrong in the plant, such as if there's power quality problems or if there's a high inrush current, then what that can do is cause other assets to trip, the switchboard to trip or something. Whereas if we're monitoring it, then it can start to give us the heads up if the power quality is starting to become slightly wrong, or if we're starting to see other issues which could cause an outage. Now, we do realize that if we're starting to now look at data, or the data gathering hub on the transformer, then we are going to have to start to think about back-end systems to manage this data. So we get the flow data coming out, we have to be able to manage it, we have to store it appropriately, we have to have systems to analyze that data. We're not expecting that the engineer gets a list of numbers to work through. We're going to have analytics which interprets the data and evaluates it. And then once an anomaly detected is seen in there, then we can start to schedule inspection. And also services can come along and have a look at the transformer. And overall, if we do this in a well-managed way, then it's going to minimize unexpected downtime. Other things we're also looking at here is the choice of dielectric. So mineral oil is it's used pretty much nearly everywhere, but now there are other alternatives which has been in service for quite a few decades now. So that's great because we have all that understanding behind us. So we know exactly how these fluids or dielectrics work. We know how to use them. So the first one we got there is the vegetable oils. So when I was working on a project about 15 years ago in Sydney, so the utility in that area was looking at the vegetable oils because they had a very high fire point, and that was seen as preferable for use in some underground substations. Another utility was very interested in its biodegradability. So they were having substations in national parks. You can't have spillages of mineral oil. So this is where they were looking at vegetable oil. So if the spillage does happen, then it's easier to clean up. There's also the dry types which are coming in. So this is more the cast resin on the right here. So this is no fluid. It's a completely solid insulation structure. So the great thing about these is as there is no fluid, then there's no possibility of spills, there's no possibilities of leaks. Now, when we think about fire safety, one of the great thing about the cast resin is obviously there's no danger of the mineral oil leaks onto the floor. And if there's a fire within the plants, which has been caused by something else, and there's no danger of the oil also catching fire. In terms of these solid insulation, the outside can char, so if it really is within the fire, then the outside surface will start to char, it will blacken, but the insulation won't actually catch fire. So that's great for this infrastructure where we really are worried about safety. So we have here, this is going back to, this is the what will happen. This is more thinking about utilities and decarbonisation. So we showed this diagram, we came up with it and we showed it a few months ago at one of the conferences. And we're more just thinking about what are the stresses and drivers do we think will be happening on our networks into the future. So we have on the left-hand side the situation now where there's little monitoring of distribution transformers, and they tend to be run to failure. So this has served us quite well for a while. A lot of these distribution transformers, if they do stop working, then it's not so much of an issue to send the truck out and to replace it. But now we're actually starting to see all these other stresses coming onto it. So we start to see at the top there, rooftop PV, the EV, electric vehicles and batteries. So we really have been thinking about how do these impact the reliability of the transformer. And then on the bottom, we got another driver, which is to do with the government decarbonisation. Now, I think one of the problems we can have as electrical engineers is that if we're designing infrastructure which lasts 20, 30, 40 years, then what are the chances of the government deciding to bring in a law or some act which changes everything? So we might find in the future the government decides to go and, well, support uptake of something, or it might decide to ban something. And then it's hard for us engineers to really be preparing our energy systems now for future government actions. So as we see happening, then we think about the costs of adapting and managing the grid increase. So once the rooftop PV comes on, then the voltage goes high. A utility might need to manage that. You might find that with these extra loads going on, the utility needs to reinforce it. Power quality might start to worsen because of the inverters, which put out a PWM wave. Now, another thing which we thought about was virtual power plants. So this isn't really something which has come in really yet. But in Australia, they're talking about people can sell their electricity back to the grid as part of a two-sided market, as they call it. So this is more where there's a price of electricity and somebody with solar might decide to export to the grid, or they might not. Now, there's ideas of a virtual power plant. So one company might get all these people to band together and they will all export at the same time, or they won't export at the same time. Now, we got thinking about what is this going to do to the distribution grid? Because right now we are designing them based around an expected diversity of load. However, if everybody now starts responding to the same price signal, then we might start to see the diversity being removed, where everybody is either exporting all in one go or they're not. And I think that's an interesting one. So we have here consequences as people start to put on rooftop PV. then we can start to see there are going to be more complaints probably about voltage problems, which then means the utility has increased costs with field measurements and mitigation. And this is then going to mean a utility has to spend more time dealing with these connection requests by checking constraints. So we can start to see that this is an impact coming in. And this is also why we're going to be leading into monitoring is useful, because rather than the engineer having to spend more time looking at all this, then the monitoring can just be providing them with the data directly, and it hopefully will increase output. There's another point here, planning upgrades with uncertainty in consumer future energy choices. So this comes back to transformers that last for many decades. If we're going to replace a transformer today, then how confident are we of the future customer load? It will be okay. Or do we have to think about upgrading maybe the amount of kVA we consider as appropriate for each house? Now, ideally, we would want the transformer to run to the end of its natural life, and then if somebody comes along and puts in a bigger one. So we would rather it does not get upgraded midterm. It's simply because that's then inefficient for the utility. Now, this is then moving into utility solutions, transformer monitoring. So this is more looking at the benefits. We've got these problems coming into the network. This is how we think the utility can actually resolve some of them. So this is all coming back to the monitoring, the data. We're going to take this data and we're going to try and do something with it. So we're going to use the data to guide their future network strategies. We want the data to speed up dealing with customer connection requests. Quite a good one is that it reduces the number of field visits to investigate problems. And overall, we hope that the data will be improving the life cycle ownership decisions, and then also provide forewarning of certain faults, such as that if we think the transformer is being overloaded or it's overheating because the load is too high, then the monitoring will let us know. So this was then the next point we move on to. We called it transformer-centric networks. Now, we're just trying to get away from this whole thought, almost like a pole top or a transformer kiosk, that it's seen as its own, like a separate thing, which is part of the network. We're more just thinking about branching out from that. We're thinking about this, transformers are at the heart of our networks. So this is just meaning that this is where we see that as it is the heart, then it's almost forming the natural hub. In that with monitoring on the hub, then we can do a lot with it. We can see a lot more with what is actually happening on our networks, and we can detect if there's any issues coming in. Now, in terms of transformers which are already there, if we don't have any monitoring on it and we have some concerns over its loading, we're not going to know. So all this is, suppose if we have a transformer somewhere and more loads get put onto it, the utility might not really know how it's being loaded, and they might just be concerned with loading it too much. Now, we think that monitoring will help save in the long run from that, because if the monitoring is put on a transformer in that situation, and if the utility is happy that the load is not getting too high, then they can keep running that transformer. Now, once the load starts to creep up a bit, then we can start to have a look at it. We can start to have a look at calculations. We can see what is actually going on in its insulation. The loading can also be used to plan our services and interventions to keep those transformers going. Now, this slide here, one which we took from Australia. Now, this is a transformer attached to a solar farm. Now, we were very surprised when we measured these harmonics, that we found these two peaks, which were around the 60th harmonic order. So these were two peaks due to current harmonics around the 3 kilohertz range. And we were very surprised when we saw them, because it lets that we can see there that there is now maybe coming in with inverters on the grid, that with the inverters coming in, they might actually start to heat up the transformer a bit more. Now, everyone, I know a lot of people use total harmonic distortion. Now, according to the IEC, that only takes into account harmonics up to the 40th order. So there's no regulation in that IEC standard on harmonics higher than the 40th. So what we're seeing here is that some of our inverter companies, they're going to start now, actually, some of them are increasing the switching frequency of their inverter, and it's pushing these harmonics up into a higher order. Now, the y-axis of that, this is just the impact on the transformer eddy currents. Now, all this is that it's a source of heat. So where we got the first harmonic order, we got a value of 1. So this is the very left-hand bar. Now, this is just showing under normal usage that this is how much heat is being dissipated by the transformer under normal use. We found when we're looking at the harmonic contents, there was 2 peaks which together were about a third extra heat energy in these eddy currents, which would then make the transformer a couple of degrees warmer, and then would actually would reduce its life slightly. Now, if we know that these harmonics are there, then we're fine, because we can do engineering calculations. We can see what's going on. Probably the easiest way to deal with this is to actually look at derating the transformer if there's harmonics on them. So we can do that by calculation. This is the other issue we've seen, is that the voltage. So as the rooftop PV, it starts to drive the voltage high. Now, most of the inverters have these set points, or these trip points, where they don't actually export power more than about 254 volts. But the problem is that if somebody's, well, that protects the system, but somebody there wouldn't be exporting their PV, and they'll call up the utility and they can complain. They can say that they're not getting their outputs, and then the utility has to do something about it. Now, this is one example where we can see a saving in monitoring, in that if the utility gets a voltage complaint, then they'll probably have to dispatch somebody to connect up monitoring to the transformer or to the site, and then decide what to do about it. Now, if there were monitoring on the transformer already, then they can download the data, and that has saved one trip out to set everything up. And of course, if they have a monitor up there, then they might have to collect the monitor at some future date, so they have to send somebody out again. So where we can see, as I mentioned here, the cost saving does depend on how far the person has to drive. But we do see that can be quite significant. When we start to see that, another thing we're starting to also see is the automated voltage control. So transformers starting to change from this passive voltage point to one which is more dynamic. Onto that. Now, this is a figure I got from one of my colleagues in Australia. So what this is saying here, so the green dashed line is the amount of PV on a particular section of their network. And then they have these consumer complaints, which they have then received, which is the red line. And what this company was saying is that as the number of PV installation goes up, then they get more over voltage complaints from their customers. So this then got the utility to be thinking, rather than waiting retrospectively for the complaint to come in, then how do they be more proactive, because they're expecting a lot of PV uptake on it. So one of them is to actually have the monitoring on the transformer, because then it warns them in advance that the voltage is elevating. But then there is other ways we can then look at on the voltage control to actually prevent those over voltages. So this is what we did about it. We have one of our transformers there. So we've now started to install on-load tap changers onto our distribution units. So this is the same type of technology as on a last power transformer, and that is an on-load tap changer. It is a mechanical device. So with these ones, they're miniaturized versions to go on a distribution unit. They come out from Machine and Fabric Rheinhausen in Germany, so it's a very well-known brand. It's been around for a very long time. It's quite good reputation for quality. And what attracted us to these units One is that there's nearly 500,000 operations that they can actually do before any maintenance or servicing is required. And I thought that was quite a good one, because obviously with these units, you don't want to be putting on devices which then require more maintenance. If something can be put on and then forgotten about, and then it runs for the whole life of the transformer, then I think that's great for everybody. So the figures on the left, this is just showing, so before the transformer was put up there, and they're starting to see these green spikes up to 256 almost volts. So then that was what people's PV starts to trip off. It can no longer export. However, these people will not be happy. When we put this transformer on it, then these voltages were kept below 250 volts. So it prevented these customer outages, and it made sure that the maximum amount of PV could be exported to the grid. Now this then comes along. So I suppose the key takeaway is that we think, looking into the future, there is a lot more uncertainty. So we're expecting electric vehicles to come in. Now technology can change very quickly, and it's even things like, what about EV charging standards? Do we think it will be the same charging standard for the next 20 or 30 years? Or do we think these car companies will be coming out with different types of standards, with different types of charging? So we can see, for us as a utility, or for us as a transformer user, it is challenging, or it is difficult to know about this planning. So we just got our thinking caps together, and we were just thinking in terms of, for us as an organisation, what would we say are the main points? How do we think a utility or an industrial company should actually be specified for the future, and that we don't really quite know what it will be? And one of the things we came up with, one was consider access to the transformer for future servicing and maintenance. And there's just been some circumstances where the transformer has been placed in a building where it's not easy to access. So therefore it's not easy for people, the services guys here, to actually get to it and to actually keep it running for longer. Another point here, I suppose it's a fairly simple one, is thermometer pockets. Now we actually are getting in questions of people wanting to retrospectively monitor the temperature of their transformer. So we think the temperature is a good one to monitor. And what we can just have is thermometer pocket. So this is just an easy access at some point in the future, where the thermometer can be put in and then it can all be connected up, and then we're relatively quick and easy to go. The next one, consider future impacts of DER. So probably the two main ones we can see from that, one is the unknown loading. So if you have lots of rooftop PV and lots of electric vehicles on a grid, you don't quite know where the power is flowing. So we can really start to think about this, and monitoring is probably quite a good one to have. Also, once we get the DER and voltage and PV going on, then it will send the voltage high. Eventually, once the voltage reaches its compliance limits, then it no longer exports. Customers can start to complain to the utility. So it's worth now the utility starting to think, how do they deal with a large number of voltage complaints coming in? Because it can reach a point where just monitoring habitually is a better option, because they're not having to send people to site to remotely gather data. And there's also the next one, consider retrofittable options. So what we're just having here, ideas is maybe if a utility does not want all the monitoring and all these smarts put onto it, is to think about how do they actually add it later on. So this could be even a couple of decades down the track. Utility wishes to monitor the transformer. It's probably an idea to think about it now. So that's the end of my presentation. It's been great talking to everybody.